Hi folks! The following video is our first one on alkynes. I'll be talking about the acidity of alkynes, ways of preparing them, and reduction reactions for alkynes. Alkynes feature a carbon-carbon triple bond, and we can think about what orbitals are overlapping to generate these bonds. Each carbon of the alkyne is sp hybridized. Each carbon uses one sp orbital to form a bond to hydrogen, and another sp orbital to form a sigma bond to the other carbon. In the carbon-hydrogen bonds, hydrogen is only using its s orbital to form the bond. Sp hybridized carbons have two unhybridized p orbitals each. Each carbon uses one of these p orbitals to form a pi bond to the neighboring carbon. This is our side-on overlap of p orbitals. And the second pi bond of the alkyne is made up from overlap of another set of unhybridized p orbitals. So the alkyne has two pi bonds, and these provide electron density surrounding the carbons of the triple bond. This electron density in pi bonds allows alkynes to act as a base or a nucleophile, similar to what we saw in the case of alkenes. In terms of alkyne terminology, alkynes that have a triple bond at the end of a carbon chain are known as terminal alkynes. The carbon at the end of the chain that's a part of the alkyne has an sp hybridized carbon-hydrogen bond. Here's an example of what a terminal alkyne would look like in a skeletal structure. Notice the triple bond is at the end of a carbon chain. This particular alkyne has 5 carbons. This position of the alkyne is 1 carbon, and this point, where the triple bond meets the single bond, is a second carbon. If you drew out the Lewis structure for this alkyne, this carbon on the end has a hydrogen attached to it, whereas the other carbon of the alkyne does not have any hydrogens. What we'll call internal alkynes will have the triple bond between carbon groups on either side. Notice that each carbon of the alkyne is connected to another carbon. And I've made the bonds for the alkyne look like the alkyne is linear. This particular example has 6 carbons. And if you draw out the Lewis structure, you can really see that the 2 carbons of the alkyne have only bonds to other carbons and no hydrogens attached to them. I want to talk about hybridization and acidity. I want to compare an alkane on the left to an alkene in the middle and an alkyne on the right, and in particular a terminal alkyne. This 2-carbon molecule alkane is known as ethane, with ane being the ending for an alkane. The 2-carbon alkene is known as ethene. The ending ene is specific to alkenes, but more commonly, this 2-carbon alkene is known as ethylene. This is its common name. And the C2H2 alkyne, shown on the right, our simplest possible alkyne, is known as ethyne. The ending -ine is specific to alkynes, but most commonly this molecule is known as acetylene, its common name. These different carbon-hydrogen bonds, where carbon has different hybridization, vary significantly in their acidities. The pKa of an alkane is about 50. The pKa of an alkene is about 44. And the pKa of a terminal alkyne is dramatically lower, about 25. Recall that lower pKa indicates a more acidic bond. The fact that terminal alkynes are fairly acidic means that they can be deprotonated by strong bases. Let's consider an acid-base reaction between a terminal alkyne and a general base. I can draw the two curved arrows for this proton transfer step. I'm drawing the second curved arrow to the end carbon of the terminal alkyne. This would form the deprotonated conjugate base of the alkyne and the conjugate acid of the base. So we want to consider how strong of a base do we need to have in order to favor the product side. The pKa of the terminal alkyne is about 25. And recall you can compare the pKa of the acid to that of the conjugate acid to predict whether reactants or products are favored. The side with the higher pKa will be favored. So because we're starting out with a terminal alkyne with a pKa of 25, as long as the conjugate acid of your base has a pKa greater than 25, your base would be strong enough to deprotonate that terminal alkyne in a way that favors the product side. I've included that general acid-base reaction up at the top, and now I want to consider a couple of more concrete examples, using NH2- as a base or using hydroxide as a base. In each case, we're considering the proton transfer to deprotonate the terminal alkyne. Both of these reactions have the same conjugate base, which is the anionic deprotonated alkyne. The first reaction has NH3 as the conjugate acid, whereas the second reaction has water as the conjugate acid. To predict which side of the equilibrium would be favored in each case, we need to look at pKa values. The pKa of the acid, the terminal alkyne, is about 25, and the pKa of NH3, ammonia, is about 38. Because the pKa of the conjugate acid is higher than that of the original alkyne, we can conclude that NH2- is strong enough to deprotonate the alkyne, and this reaction would favor the product side. In the case of the hydroxide example, we have the same acid starting out, but here the conjugate acid, water, has a pKa of about 16. The reaction equilibrium favors the side with the weaker acid. In this case, that would be the higher pKa in the starting material. So we would conclude the equilibrium favors the reactants instead of the products, meaning that hydroxide is not strong enough to deprotonate a terminal alkyne. So we can judge whether or not a base will deprotonate a terminal alkyne by looking at that base's conjugate acid and the pKa of that conjugate acid. Some examples of bases that will deprotonate terminal alkynes will be molecules where the pKa of the conjugate acid is greater than the pKa of the alkyne, so greater than 25. These bases include anionic carbons that are sp3 or sp2 hybridized, anionic nitrogens, and H- hydride. The conjugate acid of hydride is H2 gas, which has a pKa of 35. There are also some common bases that you'll see that are not strong enough to deprotonate terminal alkynes. These include oxygens that are negatively charged in either alkoxides or hydroxides. In all of these cases, the conjugate acids of these bases are stronger acids than the terminal alkyne itself. This means that the base would not be suitable for generating the deprotonated terminal alkyne. The way that alkynes are prepared is from a double E2 elimination from a reactant known as an alkyl dihalide. There are a couple of structures for these alkyl dihalides. One structure of the alkyl dihalide has the halogens on neighboring carbons. This is known as a vicinal dihalide. Treatment of a vicinal dihalide with a strong base will cause two E2 eliminations to occur to form an alkyne product. I'll show the mechanism on the next page. Alternatively, you could start out with what's known as a geminal dihalide instead, in which case the two halogens are on the same carbon. Treatment of this geminal dihalide with strong base instead will also generate an alkyne product. First, I want to talk about forming internal alkynes. Here are two example reactions that I'll draw the mechanisms for, where you start out with a dihalide with the halogens on the same carbon or on neighboring carbons. In each case, I'm treating the starting material with an excess amount of NaNH2 in NH3, a solvent. The reagent here that you need to pay attention to is the NH2-. You can ignore everything else. And the product is going to be this internal alkyne. I'm using pH to stand for the phenyl substituent. Let's consider the geminal dihalide example first. The NH2- is a strong base that can cause an E2 reaction. For the E2, I'm going to look at my alpha position as the one connected to the bromines, and the beta position, which is the one whose CH bond is going to get deprotonated. I take the base to deprotonate one of the hydrogens at the beta position. I take the electrons from the CH bond to form an alkene, and I have a loss of one of the bromide leaving groups in the same step. After this elimination has taken place, I still have one hydrogen remaining on the beta position and one bromine remaining on the alpha position. This is known as a vinylic halide. It's possible to have another E2 reaction to deprotonate the other hydrogen present at the beta position to generate the alkyne. This looks a little bit different from what we've seen in E2 before because we already have an alkene present between the two carbons, but another elimination can occur here. I would use the base to deprotonate the beta position, take the electrons from the CH bond to make another pi bond, and have a loss of leaving group in the same step. The second E2 reaction would form the second pi bond of the alkyne. Now let's consider the other variant where the bromide leaving groups are on neighboring carbons, called a geminal dihalide instead. In this case, notice that relative to this bromine, this carbon is the alpha position, and this carbon-hydrogen bond is at the beta position. I'm going to have an E2 reaction involving that CH bond on the left. So I'll deprotonate that hydrogen, form the pi bond, and have a loss of leaving group. After this step, an alkene has formed. The hydrogen on the right carbon is remaining, and the bromine on the left carbon is remaining. Now notice that relative to this carbon-bromine bond, this carbon is at the beta position and there is a hydrogen present that can be deprotonated. I'll have another E2 step, so deprotonation, pi bond formation, and loss of leaving group. And this second E2 step leads to a second pi bond and the generation of the alkyne. So in these mechanisms, each E2 step leads to a beta elimination and forms a pi bond. And because the alkyne has two pi bonds, you have two E2 reactions in each case. Now I want to consider formation of terminal alkynes instead, where the product has an sp hybridized carbon attached to a hydrogen. This is very similar in that you could start out with either a geminal or vicinal dihalide starting material, but the reagents will involve one additional step. I'm still treating the dihalide with excess NaNH2 and NH3, where the NH2- is what you have to pay attention to. But for terminal alkyne formation specifically, there is a second step necessary: treatment with water. And the mechanism I'm going to draw shows why this water is important. I'm going to draw the mechanism for a vicinal dihalide. Notice the two bromines are attached to the same carbon. At this beta position, there are no hydrogens present, and at the other beta position, 3 hydrogens are present. I'm going to deprotonate the beta position with the hydrogens present to generate an alkene. So I'll bring in the base, form the pi bond, and kick out one of the bromide leaving groups. The carbon on the right still has 2 hydrogens attached to it, and the carbon on the left of the alkene has the tert-butyl group and a bromine attached to it. Compared to the position alpha with the bromine attached to it, the beta position still has carbon-hydrogen bonds that can be deprotonated, so I'll have another E2 step. Bring in the base, form the pi bond, kick out the leaving group. This would form a second pi bond of the alkyne. One of the carbons of the alkyne has a tert-butyl group attached, and one has a hydrogen attached. So this is a terminal alkyne. So it looks like we have a terminal alkyne, but our mechanism is actually not over yet. This is because if you look back to your original starting materials, I had an excess amount of the base present. And the terminal alkyne that I just generated is a decent acid. NH2-, the excess base, is strong enough to deprotonate the terminal alkyne that I just made. So I would use NH2- as a base to deprotonate the terminal alkyne. You don't want this to happen because you want the terminal alkyne product, but you simply can't stop this proton transfer from occurring when you have excess base present. After this proton transfer, you would form the conjugate base of your terminal alkyne, where the end carbon has a negative charge and a lone pair. This cannot be further deprotonated, and this molecule would sit around in this conjugate base state until you add water in step 2. The water is necessary to protonate your anionic carbon to generate the neutral terminal alkyne product that you want. So this conjugate base of the alkyne is strong enough to deprotonate water, where water is acting as the acid here. And this proton transfer generates the terminal alkyne and hydroxide. And recall from earlier that the hydroxide is not strong enough to deprotonate the terminal alkyne. So after these 2 reagent steps, NaNH2 and water, you get that desired terminal alkyne product. I want to end today's video by talking about alkyne reduction. Reduction referring to the addition of hydrogens to the alkyne. We've seen hydrogenation before in the context of alkenes. Recall that an alkene can be treated with hydrogen gas in the presence of a metal catalyst to generate an alkane product. This occurs by syn addition of the hydrogen. In the case of alkynes, treatment of the alkyne with hydrogen in the presence of platinum or palladium on carbon or nickel will generate an alkane product. You can assume that there's an excess of hydrogen present, even if it's not written that way. So in this reaction, you've actually added 4 hydrogens to your molecule, 2 at each of the carbons that were formerly sp hybridized, to get to that alkane product. The alkyne is first reacting with hydrogen in the presence of your metal catalyst to generate an alkene. But as we saw previously, alkenes react with hydrogen in the presence of the catalyst to generate alkanes. So essentially, it's hard to stop at the alkene under these conditions. You'll form the final alkane product instead. There are ways to add hydrogens to an alkyne to generate either a cis-alkene or a trans-alkene selectively, but we need new reagents to do these things. To form a cis-alkene from an alkyne, you would use a less active catalyst than the metal ones that we learned previously for alkenes. These are known as poisoned catalysts. Examples of ones you'll see in the textbook are known as Lindlar's catalyst. This is a poisoned palladium catalyst, or a catalyst with 2 nickels and a boron. So what your reaction would look like is starting out with an alkyne and treating it with hydrogen, either in the presence of Lindlar's catalyst or in the presence of Ni2b. In each case, these reagents promote the formation of the cis-alkene product. So you've added a hydrogen to each of the carbons of the alkyne on the same side to generate the cis-alkene. In the case of forming trans-alkenes, you'll use conditions known as dissolving metal reduction conditions. These reagents will be sodium metal and liquid ammonia solvent. So be careful, these are not the same conditions as NaNH2 and NH3. This is sodium metal with an oxidation state of 0 rather than a sodium cation. So what this would look like is treatment of your alkyne with sodium in the presence of NH3. It may or may not be included that this is a liquid, but just know that it is the liquid form. This reaction will selectively add 1 hydrogen to each of the carbons of the alkyne, and it'll do so in an anti-manner, meaning you'll form a trans-alkene product. So for all of the reduction reactions I talked about here, the full hydrogenation to generate an alkane, or the partial reactions to generate cis-alkenes or trans-alkenes, in all of these cases, I want you to recognize the reagents, be able to predict the products, or be able to provide the reagents necessary in a synthesis reaction, but you do not need to know the mechanisms for these. All right, so in summary, today's video introduced alkynes again. I talked about their structure and the acidity of terminal alkynes in particular. I talked about using elimination reactions to generate either internal or terminal alkynes, and I talked about reduction methods. That's it for this video. I will see you in class.